Hi everyone, and welcome to this Twitch session from the Data and AI Academy, the Data and AI community from the ERNI Academy. So today we'll be talking about the GeoML project that our Swiss colleagues have been developing. Remember to check our previous session that we made two weeks ago about women in data, where Sarah Langas talked about data engineering, how to build a data lake from scratch. You can find this session in YouTube, the YouTube of the ERNI Academy. So feel free to follow also the YouTube channel. So this will be a discussion talk, not a programming session. So you won't see you won't see any code today. This will be we'll make them some questions about how they develop this app that we'll be showing now in a moment. Also, remember that you can make questions during the session or at the end of it. So you can make questions in the Twitch chat. So let's start with the presentations. So please, Michele, if you want to start presenting yourself, please.
Yeah, I'm Michele. Well, I'm here from the office in Zurich, Switzerland, and from my background, I work at ERNI as a data scientist, and my background is in mechanical engineering, where I was working in energy technology, and I did my PhD in modeling of combustion system for ship engines, of those very large engines, and did a lot of modeling work, a lot of data and modeling. And what brings me back to data science in ERNI is the interest in trying to find use cases in general and to use those analytics tools. And we will see more today.
Nice. And also, Thomas, if you want to introduce yourself, please.
Sure. Hi, everyone. So my name is Thomas. I'm also a data scientist here at ERNI since a year roughly. And my background is in physics, especially in astrophysics, where I did my PhD in simulations of galaxies and black holes. And I started to like data science because I had to deal with a lot of data, modeling, huge simulation runs, and this is what I found very interesting in finding new insights, generating new models, and really play around with data. And during my PhD, I came then around through data science techniques that I used, and it made just a lot of fun, and that's why I'm here now at ERNI, and I hope we can share with you a little bit of GeoML.
Great. So, well, maybe you, before going further, you can explain us a little bit of how is this transition from being a PhD, a scientist, to a data scientist. That it's a kind of scientist, but maybe there are some differences. If you want to explain us how this journey has been.
Sure. So yeah, it is quite different. So I think in the industry, it's really more structured. It is way more organized than in academia. So in academia, you really try to find new things by thinking out of the box, trying to really tackle problems in not the proper coding way, and you just try different things and you really try to get along as fast as possible and really cut corners also at some points, that you don't code very cleanly or that you don't write documentation. And of course, this is quite different in industry. So here you work in larger teams, not in a PhD, you mainly work in a big collaboration, but most of the time you work on your project on your own with your supervisor. And in the industry, it's the other way around. So you're part of a big team and everyone needs to know your work. You need to document your code. You need to share your code. And this is just a different way of thinking. But the main problem is the same. You try to solve problems. You try to solve problems efficiently. And you try to find very good ways of dealing with certain things, right? So you have to always keep thinking, you have to come up with new ways. And I think that's very, very similar. It's just how you handle a project, you do it differently. And you don't write papers, you write documentations. I think that's also like a slight difference.
Yeah. Also for you, Michele, how it was this?
Yeah, let's say I came from mechanical engineering and Thomas from physics, but I can confirm 98% of the impressions. And let's say it starts with the name. If you say research, it doesn't mean to find something. It's more to search and to look for something. And It might sound a bit philosophical, but there is something up there. And if you have a project during your PhD, you are alone in the sense of trying at the edge of knowledge, and you try and you need some fantasy, and sometimes the communication is very different. For example, if you say, okay, here in 2 minutes you present yourself, you need to come to the point straight. And in research, people have a bit more time, and then they tend to be more detailed, affine, let's say, put it that way. And yeah, but this is a very, very nice trip, and also the transition. Not easy, but very interesting.
Yeah, so thank you for sharing your experiences. Really interesting. So, Ayose, if you want to follow with the introduction of yourself, please.
Yeah, cool. Hi everyone. I'm Ayose Iturralde. I work in ERNI as a data principal in Spain. So my main role is like be the technical leader of the data projects, the end-to-end projects that we have, or projects that are more focused in data engineering or data science, even data visualization. My background are maths. I'm a mathematician from my studies, and then I did a master in big data and data science, and well, I didn't have the luck to work in the research I will like, but I didn't be able. So I started working like 5 years ago as a data scientist in other companies, and then I arrived here at ERNI like 6 months ago, and well, that's me.
Nice, thank you. And finally, I am Enrique Domingo. I'm a machine learning and software engineer at ERNI. I work for a pharma project currently, and I co-founded a drone startup around 7 years ago. We started, and I was during 5 years dealing with software, flight analysis, and also computer vision for drones, a little bit of everything there. And yeah, now I'm at ERNI as a machine learning engineer. Okay, so that was more or less the introduction. Also mentioned that we are from the data and AI community at ERNI, and we meet internally with some other colleagues like once a month, and we share some technologies, some experience that we have. So every month we talk for a different topic related with data or AI. And at some point, some months ago, Michele mentioned that they were starting this project, and when he explained me about it, I found it like really interesting, a really original project. So maybe it's time to go for the demo of the application that we are talking about, the GeoML demo. Okay.
Yep.
You have it there, Ayose? Okay.
Yep.
So let's see what we find. Yeah, let's see what we find out when we go to the GeoML ERNI webpage.
Let's play the tutorial, right?
Let's go. The introduction video to learn how to play with the challenge. Okay, so that was more or less the intro of it and explaining how to play. I shared here in the chat the link to the app, so if anyone wants to try it, and just tell us how has been your experience and your score compared with the one from the machine learning algorithm. I will share also the link for the datascience.erni, the data science website from our Swiss team there, just if you want to check their info and so. Okay, so if you want to start explaining us about the application, please.
So yes, I think either Ayose or someone in the chat would like to take the.
Yeah, maybe we can play last one or one.
Okay,
and
let's start.
Maybe if someone in the chat want to check it and try to beat the model, we can work like that. And if there is not any answer, I will try to play.
Okay. So the idea is, we see here this image of this map of it's from Switzerland, and we have to decide from 1 to 5 how risk it seems to us, isn't it? So
yeah.
Well, let's do the first one just to see it. So Ayose, if you want to bet on this one.
Yeah, if anyone in the chat want to make a
let's do us the first one, and let's let the second one for the people in the chat.
So, well, I think that there are just a straightforward or more or less a straightforward road with not too many crosses. So I will go for a 2, but I'm not sure. I don't know anything.
Okay.
So
let's see it. Okay. So correct answer was the 1, isn't it?
It was the 1 exactly, because there actually I cannot see it on the screen, but I think there were no accidents, so it was really a 1.
Yeah.
And in that case, actually, also the neural net actually guessed a 3.
Okay, so in this case, we made it better than the neural net. Let's see
Yeah,
if this
exactly.
Yes.
Let's go for the next one. Now let's leave people in the chat to bet from 1 to 5. Let's see who is the first to bet for this one in the comments. Otherwise,
let's wait 10 seconds, and if now one, I will. I mean, I was lucky, so maybe I can try to beat the model.
Let's leave these 10 seconds to, if you want to explain, please, who was the team that created this. So you two, but I think that you weren't the only ones in the team that created the GeoML application.
So yes, we were definitely not the only ones doing this app. So we had the data science team at first, where we tried to do it. The 5 people of us in the team were trying to come up with the challenge, try to go through the challenges itself, like how to get data, what to do, which we will explain later as well. And then of course you can see that we also have a nice front end. We had some UX designers who helped us with the interaction with the people, and we also had some people from marketing who wrote actually with us an ebook and distributed this game also via LinkedIn. So it was actually a big team behind it. So it was not only the 2 of us who are today talking, but there were many people involved, and we can discuss that later once the game is done. That we can actually discuss that.
Okay, so thank you for the introduction.
It goes for 2, so let's see.
And this one that made better. Okay,
it's really difficult. I play 3 or 4 times and never beat the model, but now
but this time we are getting
we are so close in the first, like we are having a demo.
Let's see for the next one. Okay, let's let 10 seconds. If anyone wants to guess this one,
let's wait for Rocket Money, or who wants to try make a guess.
So you told me, Thomas, that you played many times while testing and building the application, and you never won the model. Maybe sometimes, mostly, you were close to it, but
sometimes it was close. So I played really very often. Sometimes you get very close. With time, you obviously also get better because you start seeing the patterns, what's going on. But yeah, sometimes I maybe won 1 or twice, so not very often. But there are certainly occasions where you can win. So it's not fake. As you notice, we are not trying always that the neural net wins. But yes, the neural net normally wins, and it's actually in normal occasions, I think it beats us humans. But let's see. Maybe we are lucky.
Maybe it's the first time. Okay, let's go with the 4.
Rocky Money
Rocky
goes
Money
for number 4, so let's
check it.
try.
Okay, this time it's a bet. The true
Yeah.
was the true one was the
We
third one.
worked
Okay,
on the model. Well, we did almost the same, right? Because the
Yeah.
correct answer was 3.
Our error and the model one was the same. Only one of difference.
Exactly.
Let's go for the next one.
So
Anyone else?
Rocket Money, you are being so
and those,
accurate.
keep in mind, these are data from Switzerland. It's a lot of green stuff and curves and so on, but also the driving style is the Swiss one. So not sure what's the difference compared to other countries like Spain, but that's actually, you need to have the Swiss driving mindset in mind when you try to tip on the risk level.
That's also a topic for later, I think. How transferable is this model to other places? But yeah, let's discuss this at the end. Okay, I will go with this
maybe
one.
I can go for the last 2 ones in order to be faster, and then we can start talking about how do we deploy the model.
Okay.
Okay. So this is like a straightforward middle of the mountain. So I will go for number 3, maybe middle.
Okay.
Oh,
that was pretty safe.
My bad. So Rocky Money are better on the model, but not me. And this is, for me, it's evident that it's like a 1. It's just straightforward, 3 different lines. So
okay.
Oh.
It was true. So here we can see the spots are the accidents that we didn't mention it. So we see here the map, the roads, but also the accidents are these spots there. Then we can talk about the color of them or what do they mean. Okay, let's see the final.
We can explain that maybe a bit later when we open again the game.
Oh, we won.
And
we won.
Yes.
Maybe it's the first time that I see that we won, like a demo effect.
Okay.
So actually now we have it on record so that you can actually beat even the game. So when you play it later, you really see it's not staged or anything. You're really playing against the neural net, and it's not like that you always lose.
Yeah, now you need to stop if you want to keep your 100% record. Otherwise, it's going to decrease quite a bit.
So if anyone else is trying it at home and wants to share the results, please. So most of the times I tried like 2 or 3 times and I was losing all the time. So it's the first time that I see it winning. But if someone else has some scores, please share it on the chat. Okay,
well, it seems like more than one mind works better than the model. If we can ask for different guys for different situations, so maybe we can start talking about what you did, guys. So I will stop sharing my screen.
We were here with a large ensemble of different minds. Maybe was that the thing?
I don't know why I cannot stop sharing right now.
Okay, now. So let's do some disclaimers first of all. Also, so this application is an internal project from the Swiss team of data science. So this is not a real project, and this model should never be used for determining if a road is safe or not, or to define new roads. It's just a proof of concept to understand what are the possibilities of the technology and to understand a full pipeline of a data science project. But it's not a real data science project. Also, it's not applied under any customer, or it doesn't have any revenue. So they haven't spent much in deployment of them or in the development of the application. Just to be clear. So if you see there some road that the model says that it's not safe, maybe it's not true. Okay, maybe the model is wrong. So it shouldn't be used for that, isn't it, Thomas? You were telling me that before.
Exactly. So it's really, don't take it too serious. It is mainly how we defined risk, that we actually showed what is possible. But again, it's not like that you should not step on those roads or talk about risk. It's more like what can you do with a CNN?
Yeah, if I would add at this point to say Switzerland has a lot of open source data, and this was also an occasion for us to see, okay, from a data perspective, you say, okay, it's like Eldorado. You have a lot of data and so on, and what to do. And for us, what was important is to have a relatively lean project with all the building blocks of a data-driven project, so that we can use it with open source data, but also software, and to show what type of challenges. And also we try to basically document these and condense into an ebook where we can say, okay, we have all the elements, and so that we can see, okay, which type of competences and which type of pitfalls do you need to keep in mind, because this is where the experience plays a big role. Yeah, so this was basically a transparent way using non-proprietary data for showing this type of stuff, and trying to be also kind of entertaining and user friendly. Yes.
Yeah, so as I mentioned before, when you explained me this idea, I found it very interesting and very original to find these three sources of public data and making something useful of it, not predicting something without any sense, but making, and also finishing it with a challenge, not only with a normal prediction app, but also with a challenge that you can compete with a machine learning model. Yeah, as I mentioned, it's not to really determine if some road is safe or not, but yeah, it's a demonstration of technology.
Exactly.
You can share the ebook.
Yeah, sure.
Yeah.
Give me a second.
What we also want to say is we also see it as a part of data literacy, where we basically want to educate people, right? In a sense, what is possible, and also it's much nicer to have a challenge hands-on, where you can actually experience it firsthand, than actually read about risk or look at some dry statistics, so that you can rather actually learn it by yourself, or actually get experience how you can define risk, what are the math formulas behind it, without actually going through the mathematical details or the plots on dry numbers. So that was also one of the ideas.
Okay, so
there is a question in the chat that maybe is not clear right now, but I think you already explained is which data did you have? Because Rocky Money asked if is the model based on traffic data that was present at the moment, or photograph, or based on the image to predict the risk?
We can go to this point now in a moment, when we will be talking about the data of the project. That is maybe one of the first points of the project. So let's just start maybe with the use case, the identification of the use case, and then we'll see the data availability probably from the ebook structure. So
yeah, I can actually, as we were saying before, the use case was to find let's say, like, minimal viable, let's say, instead of project, where we can say we have all the functional building blocks of data-driven projects, and we can basically sensibilize for this type of what to look at and so on, in a way that is somehow has some sort of beauty, in the sense is not necessarily you have a big gun and you do huge machines, but actually you try to do it in a lean way. And regarding the data that we took, we did it in a conscious way to make it to take publicly available data, so that we don't have issues with sharing it with people and so on. And regarding the content of the data, this, as I said before, Switzerland is like a very, very diligent in terms of collecting data, make them publicly available. And what we used was the statistics of the last 12 years in all Swiss streets of geolocated every single accident with some person involved is geolocated, and then we took all of them. And in addition, what you need is to know where are the accidents. So we are talking about something like 200,000 geolocated accidents. And you need to know where are the streets, basically where are all the roads. And the other one is you need to know how many people and how many cars drive on the streets, because actually the risk is, we define it as to say, okay, how many accidents per vehicle and kilometer, because this is actually one way of describing it. So basically we need these three elements: where are the accidents and how many, where are the streets, and how many cars on average every day do they travel on this road. And this is then enough information for creating basically this data set for risk of every street in Switzerland.
Exactly. So actually, I might add, Michele already said it just very briefly, but one of the challenges was actually not only getting the data set, which was already difficult, like how do you make those images, how large should be the images, again, are the geolocations actually of the accidents on a street or not, what is fine enough that is not being on a street, maybe it happened on a sidewalk and it's not really like a meter on the street. So these were all like very difficult challenges, but I also Michele already, because you worked so long with it, defined what is risk, right? There was also a question, how can you actually define risk? So you came up with many different ideas. Is risk maybe how many accidents do happen? How many, because we also have different categories of accidents. So should we weight them according to the heaviness of the accident? Or how many people drive there? How many cars are driving there? How long are the streets, right? Because certain roads are maybe or certain images, sorry, have multiple roads on it, right? So it's not fair to just categorize risk per image, but per how many kilometers you have on that image. So Michele just already said it while explaining what the data sets are, that we actually defined risk by weighting how severe the accident was, divided it by how long you can drive on that road and how many people drive daily on that road. So you could actually imagine that we somehow, it's not fully correct, but somehow we tried to ask ourselves the question, how long can I actually drive on that road, on that image, without ever happening anything?
Okay,
And
so
that's
the final metric. The final metric is this score of the risk of a road, and so how you define it then? It's the like per kilometer. So how will be the formula? Like how many accidents by the risk of every accident divided by the distance of the road, or something like that?
Right, it was nearly correct. So it was how many accidents happen. So if very minor accidents happen, we don't weight them. If there are severe accidents, we weight them by a factor depending on the how bad the accident was, and then we divide really by the kilometers on that image, and divide by the number of cars that drive there in a day. Exactly, that was
Okay.
Yeah, basically you could interpret this as, for example, in Switzerland, cars, they drive on average around 12,000 kilometers. Let's say this is like you take as a sort of amount of driven kilometer by a person every year, and then you look how many kilometers statistically you get an accident in different places, and then it means how many hours or years statistically you would travel. Is not necessarily bounded on one person, it's more a statistic. So basically you can get the same sort of risk with very few accidents with few traffic, or many accidents with a lot of traffic. So basically you need to keep in mind there are three elements here, and this makes it not very intuitive sometimes, because maybe you see something very straight and you say, okay, nothing is happening. But for example, in the roundabout, it's very interesting to see where accidents might happen, but actually depends very strong on how much traffic there is. And there are so many elements, and it's also fascinating how the algorithm can deal with this, because For example, here on the screen, you see 4 different layers for GIS information. The first one, is the upper one, is a satellite image. And maybe as a question, do you know where it is? Because this is very characteristic. It is one city in Switzerland, maybe.
Okay, now you will get me because I've never seen yet in Switzerland. I don't know if you, Jose, know it or
No,
someone in
This
the
is
chat. Someone in the
I
chat
don't
has been
know.
there.
Honestly, I don't
if
know
you would
anything about
zoom in a
Switzerland.
bit more, you would see the jet d'eau. It's a Geneva. You have this
Okay.
high jet, which is like 100-meter high, and basically this is an image of Geneva.
Okay.
And in the lower layer, you have all the streets and the cars and how much traffic and where the accident took place. And this is more
So let's go one by one.
iconic image.
Let's go one by one through all data sources. So we have the satellite images. This is the first picture, isn't it? So where did you get the satellite images from? Which API or which source?
So let's say we are back in Switzerland, where there is it's called Swiss Topo, which is the federal office for topography, where they have a very detailed aerial image, which with a spatial resolution of 10 centimeter, which means Switzerland is not very big, but if you cut it into 10 centimeters, you end up with
a lot of pixels. Yeah.
a lot of pixels. And if you say, okay, how many terabytes it is more than one. We are in the order of a dozen terabytes for one image, which means already we can talk about big data, because I don't have 10 terabytes of RAM on my machine. Unfortunately. And it starts there to say, okay, you have an API, but actually, even in this government data, they have an API, but actually it's not that easy to download the data, because, for example, even for them, it's very challenging, because, for example, you say you can cut a place, and then they they section every square kilometer with index, and basically they give you like a CSV file of every square kilometer in Switzerland. Then you need to select which one, and then you get a link for downloading, and then you get all the stuff, and then help yourself. And then say,
it's a
put
really
this stuff together.
a really interesting data pipeline there, dealing with probably pandas to deal with these CSVs, and then extracting, downloading these URLs of every the location of every tile of every image.
Actually, there is GeoPandas if you want to know it. And if you work on GIS, it's going to be one of your Raster.io and GeoPandas might be your two buddies. Yes.
Okay. Like NumPy and pandas normally, so GeoPandas.
No, because actually the information is georeferenced, and even to know how to reference images is very tricky, because, for example, there are projection coordinates, and, for example, in Switzerland they have a dedicated coordinate system, which is called LV95, which is a projection which has the best approximation on average for Switzerland. Basically, this is also a very GIS, let's say, heavy procedure. And Switzerland is very famous for this type of GIS. And for example, shape files and all this type of formatting has a lot of root in Switzerland for the mapping.
Michele, for me, it's really fascinating as a data scientist that has this amount of information as a public information. Maybe in Spain we are not so lucky for that. We have kind of information, but not as well managed as you. I would like to know the quality of this data. Is you were talking about the geolocalization, that it maybe is not so accurate sometimes, and you have to make some transformations. Did you face any other problem with this data, or was the quality enough to keep going with this proof of concept?
If I might still, because we are on the preparation part, let's say I was more heavily involved in the cleaning of the data, the collection, to see whether the quality is high. And let's say people say on average is 80% of the work, and the funny part, the algorithm implementation and so on is that, well, in this case, we are happy. We are very, let's say, lucky in Switzerland because there is a culture of quality assessment and the versioning of data and so on for this type of data. And there is like a Swiss open data platform, and there are something like 8,000 data sets, 8 with 3 zeros, which is a lot. And this is just one example. And in terms of the accuracy, you need to be very careful because you have streets, then you have a model-based traffic information for different, weekdays or rush hour and so on, and geolocated information of the accidents, and those ones are the police department is responsible. So basically, different departments are responsible for different type of data. So basically, you as a data scientist, you need to bring your flair for sanity checks, because you need to have a feeling for how much quality do you need or what makes sense, because then it will have an influence on everything. And maybe Thomas will tell more. He can tell you really books and books, volumes about how to define metric and the binning of samples. This is actually data science for me.
So,
just to highlight what Michele was just saying, actually you can see the impact of what was Michele saying when you play the game. So maybe when you play it, you see that there are multiple streets, but only one street is white. So that's the street we are concentrating ourselves on, because for that street we had all 3 sources of information. So we had the traffic information, we had the street information, and we had the satellite image.
I was about to ask you. So we only talked so far for the satellite images. So I think that there are more sources of images. So which others? You mentioned like the roads information and the traffic information.
Yeah, well, that's, I would say, if I would be to guess, this is unique. Let's say in Switzerland is the only place where you get all this type of granularity of data. So in this sense, let's say, where the roads are is basically a static image, basically georeference, where you have lines everywhere. The location of the accidents, you know where, when, and the date and the place, and how heavy it was, and which type of reasoning for the accident, the cause. And for the traffic is basically, in Switzerland is small, but they have something like 5,000 automatic places where they measure the traffic in real time, basically at a sub 1 minute resolution. And then they have a model, a network model, which basically assimilate everything, and then as a flow, and with agent-based models that gives you, basically, it fills all the gaps of the traffic, which is a huge work. We didn't do this work, but we had accessible, because this model-based data is open source. So basically, we could match everything together. Yes. This is the difficult part of the quality of the data, and yeah.
So there are like 4 sources of information, as I understand. The roads, that is a mask, is an image like a mask with the roads, and then the traffic, that how is the traffic defined, and how do you call it from the API, yep. Or how do you have it, the traffic?
Basically, you have a shapefile, which means is a long list of georeferenced points, lines, polygons. And then basically you have something like 1 million streets segments. And for every segment, it means is from one cross to the next one, so that it is uniquely defined. And for these 1 million segments, you get values for during the weekend, during the rush hour in the morning, in the evening, or during the week. And basically is like an attribute for all of those 1 million segments. And then basically you need to know what do you want to do, because this is basically the full mountain of data. And then you need to think, because streets are not everywhere, because there are a lot of mountains, and sometimes it's a bit sparse. And then you need to go back to the model to say, okay, what does the model need? Because this is the data itself. And I guess this is where I would give it back to Thomas, because this is only the start, actually, of this data-driven project.
Yeah, so maybe we can go to the next point in the ebook. So we have been talking so far from the data sources and how we get this data. So I just, if you can scroll to the next, I think it's the data quality. Well, we talked a little bit about data quality. I don't know if you want to add something else. We already talked about it, maybe.
I think Michele perfectly described it, what the data quality has to be or how it is in Switzerland. So I think we covered that. So we can continue.
Actually, I would go to the number 4, which is definition of the metric. And this is where the magic and the experience is basically data scientist made. And this is where Thomas, it was the interface between myself and Thomas, because I did all the heavy work in cleaning and doing, and then basically giving to him a lot of data.
So you were more a data engineer. You will define yourself more a data engineer here in this project rather than data science, or machine learning engineer, maybe something around there.
I think you can really not define the roles, because in the end we really communicated quite a bit. So yes, Michele did the data cleaning and the data gathering, but I wouldn't make those strict distinctions between us, because also he had a lot of say in what kind of data we need. He exchanged with me what I need with the model, and the other way around. So I wouldn't make this clear cuts in this project, at least.
Okay.
I would call it agile in the sense of there is not strictly the project organization, but in the sense I had an idea. For example, I tested, I collected data and put them together, and then I gave it to him, and the model was doing great. Maybe sometimes it was overfitting, but for the wrong reason. And then we basically, looking into the results, we start understanding, wow, how do we collect the data? How do we distribute them? And then basically this was the loop between the two of us. For example, that everything is interconnected. The metric, the quality of the data, how do you define the risk, or how do you sample it? And basically this was I would say very strong data science, the essence of it.
Normally in a good
scientific work.
Okay, so normally in a data science project you have these loops of validating a hypothesis, validating data, and going back because maybe it's not enough, and you need new data, redefine the metrics, redefine the problem, isn't it, Thomas?
Exactly. So actually, what Michele was already as well saying, we actually had one data set where we had really great predictions, and then we found out that actually something was wrong in the data set, right? So that we had overlaps in images, and that the algorithm was
too good to be true.
Yeah, exactly. So you have to also be critical, not to say yes, we match, we predict like 90%, but we really tried to figure out why and what is going on. And that's also now the metrics part. We were describing what is risk, but as you've been going through the challenge, you noticed that there were 5 buttons, right? Risk from low to high. So we had to come up with categories also for the neural net to label them. And so that was actually quite challenging, because you had to figure out the basis in which you distributed the data or the risk equally, so that you actually, when you run the challenge or the neural net, so that you could interpret the results, right? Because if you have everything just in one major bin and the others are very sparsely distributed, your network would somehow learn that 90% of the image are just in that label. And so it's not very purposeful to run a neural net like this. And that's where we had a lot of exchanges, how to clean the data, how to make the images, how to make a proper label for each image, and how many categories do we actually need to have.
So maybe you find this out in the exploratory data analysis. Maybe you find you were exploring the label and you find out this way of classifying the risk. So normally it's done in the EDA, the exploratory data analysis, isn't it?
Yes. So not only exploratory, because for example, it was also
Prototyping.
how big are those image cuts that you made, right? At some point, we had to decide, do we want to have 500 meters, a kilometer, 200 meters, 50 meters? Because as Michele said, you have a resolution which is incredible, but then you have downsides. If you have a huge resolution, your neural net cannot learn because it's simply too heavy to compute. Or if you have it too coarse, it will learn nothing. So it was a back and forth between the two of us. And imagine if you make your cutout too small, you have many streets where nothing happens, right? Because you really have just a street going through with cars, and there won't be any accidents. And then you have streets which are super cluttered, so you get very big jumps in your labels, which is also not good. So you had to find a middle way, and this was where we communicated quite a bit.
So what was at the end the final way to distribute these labels in these 5 levels, more or less properly balanced?
Do we have 1 week time for explaining?
Okay. Like
no, but,
summary,
okay. So I can tell you actually in the end we chose a logarithmic base of 4, which basically means that if you go between each level, the severity of the risk should increase by 4. So going from one level to the other is 4. Going from one level 2 levels up, it means a factor of 16. So that was the.
It's like the seismic levels of earthquakes. Maybe people is more related to that. So it's not a linear scale. Okay.
Exactly. That the severity of earthquakes would be log 10. So in a 10 basis,
log 4.
Okay, base 4. Exactly.
Okay. Like first maybe it's 2, then 10, then 50, and then 100. More or less. I don't know now the log 4 scale, but just to give an example. Okay.
No, it's a perfect idea. Yes, exactly. So that was also where we spent a lot of time, and that was also connected to the cutout of the image.
Okay. So we are now seeing these tiles, these image tiles. You mentioned that you had to downscale them so much because they were in a so good resolution, like 10 centimeters per pixel, and maybe here it's already downscaled. And when people is trying the challenge in the app, they will see that they are pixelated. But this is because then you could train this in the CPU, I think. So
Yes.
Did you use a CPU or GPU?
No. So for now we really use CPUs because I planned a lot with different neural nets, which we wanted to use. So it was convolutional neural nets, and we had different structures. So one famous one is AlexNet, but we then in the end used the efficient net, and to be very precise, it was the efficient net B3. Why did we choose it? Well, a lot of trial and error. Also, like we tried to write our own net and all those kinds. So we did a lot of testing, and in the end, what we found out, a very good balance between accuracy, computational time, and the prediction actually was that we had a lower efficient net, so that we can calculate it with a resolution, I think, of 128 pixels in each side. And that was actually a very good sweet spot for the network to learn. We did then the test with 32 pixels, 64, and 256, but the sweet spot turned out to be 128 for how long it needs to train and show very good results in the end.
So normally a machine learning model it can have two main how it's called or classification or regression, two main tasks. You can have a classification problem or a regression problem. Classification could be like predict me if this is a cat, a dog, or a fish, let's say, like separate things. And regression is like predict me the temperature of tomorrow. Okay, 0 degrees, 10 degrees, 15, a continuous line of numbers. So how did you put this in the model? Like a regression problem or a classification problem?
We actually did a classification problem. So that's why we actually made those 5 categories, because we wanted to see if you can actually get roughly the idea what kind of risk it is in a broader sense, right? We didn't want really to get a number that's the specific risk, but we just wanted to know, can such a convolutional neural net, which is actually impressive because you just look at a satellite image with no other information, and you can actually somehow classify what is the risk of that image. So there's no information about how many cars are driving. There's not information about what kinds of accidents happen. There's nothing. There's just this image. And so we thought it's already challenging enough just to get roughly the idea right, then actually to predict a certain number.
Yeah,
So
I think that
that's why
both
we
could
thought-
be done. Both could be done. It only depends in the strategy of the metric that you define. So for this reason, I found that both could be possibly. Sometimes you can only do one or the other. Most of the times, but in this case, you could do both. I don't know, Jose, if you have any experience with this kind of problems with regression or classification.
Well, yeah, I was working with a couple of regression models. But I don't know how to. I'm able to share or not about that. Maybe the most typical thing is like making some regression. It's not exactly typical regression, but ARIMA models and whatever in time series, whatever to make a stock prediction on sales and these kinds of models that are really interesting. I think we have a question from the chat.
Yeah.
From Rocky Money. Can we make the model predict possible coordinates for high chance of accident based on real-time traffic data? I mean, our model is able to work on real time.
So, do you see the question, Thomas?
No, I don't see the question, but I heard it. So maybe we can repeat if we understood it correctly.
Okay.
Whether we can make basically a real-time prediction. Let's say, okay, what's the probability tomorrow in this street something will happen? We can, let's say, the answer is no, depending what means real time, because actually, as we said before, we had 12 years of accidents data, which means it is historic data. This means we don't have enough, let's say, accidents. I mean, luckily, let's say, from the topical perspective, because actually, if you have 1 million segments of roads, and then you have a couple of thousand, 100,000 accidents, you cannot have a resolution in space and time, because otherwise you don't have enough samples. So basically, the answer is no. You can have a probabilistic view to say, okay, in the next 1 year, this is this probability, which means basically you can translate the risk into a probability, and then you can narrow it down to 1 day. But actually, to have let's say, decision to say yes, no, is actually too. You are in the noise of the signal, basically.
Exactly. So again, keep in mind that we are not trying to predict anything or say don't go on this road because there will happen an accident or anything. It's nothing like this. It's very statistical, as Michele put it. So we really just it's on average on historic data. It doesn't mean that anything will happen tomorrow or the day after tomorrow. Again, it's very statistical. So don't be afraid to go on the streets that are high risk. Another thing that we should really point out is because so few accidents happen, what actually can happen is that if you're on a road where people don't drive that often, and suddenly there happens an accident, that you move a few classes up and down. The reason for that is really, again, we are very lucky, not many accidents are happening. And so if you have a mountain road and somebody drives off the road, the car is slightly damaged, this road would be already classified in our approach as more dangerous. Because again, not many accidents are happening and not many people are driving on certain ways. So again, take it all with a grain of salt and in a more probabilistic point of view.
Actually, we took, regarding the data itself, we took a threshold to say what is a minimal daily traffic rate for taking this street as statistically relevant. Because actually, if we I don't remember exactly the number, but if you say if we have 200 cars per day in one segment, if it's less than this, we basically delete the accident happening there, but also the street itself. So basically, we try to basically remove very sparse data where statistically it is very noisy, because one accident will have a huge influence into the statistics because it is too discrete.
Okay. So also, I think that we mentioned that we have like this traffic information and this roads information, but probably it has only been used to define the labels. So the inputs of the model are only the images. So the model only knows the image. It doesn't know this historic information and all of this. Maybe with another architecture and another strategy, if we put with a very more complex model, not only the image, but the image through all and the time series of the accidents, the traffic, maybe we can reformulate the problem and approach to that, like in a given moment with this given traffic. But this is a different problem, so much difficult, and maybe with many more grains of pins of salt. But yeah, in this case, this model couldn't do what Rocking Money said. Okay, so maybe we can go to the next slide and talk a little bit more about the algorithm, the model. So we mentioned it a little bit, but first of all, it's TensorFlow or PyTorch? What have you used?
It's TensorFlow.
TensorFlow, okay.
Yes, exactly. So we use TensorFlow. So again, as I said, we won't go into very geeky details right now, but in principle, we used a couple of architectures. As I mentioned before, AlexNet was like the first thing that we thought could work, and we saw really, really different behaviors. We even tried to scale down AlexNet to our problem, so not use the out-of-the-box AlexNet, but have our own version of it. We tried to rewrite the loss function in TensorFlow so that we had a custom loss function. We tried to train weights from scratch. We had pre-trained weights, and so we had all to weight all of this against each other and found the optimal algorithm in principle, because we were set that we simply want to show that by looking at images you can already tell a lot, and that the neural net is actually capable of that. So we were kind of, from the beginning, we were trying to use a convolutional neural net just from the get-go, that we can work from the images. But even if that was already defined, you had a lot of possibilities to change the algorithm or the net. And as I mentioned before, we actually decided on the efficient net with pre-trained models, and to be weights. And to be very precise, we used the noisy student weights, which was really a huge improvement over the standard weights.
Okay, really interesting. This is called like the hyperparameters tuning in a machine learning project. So yeah, it happens many times that you think in a computer vision problem that your problem is so special that won't fit in the pre-trained models that usually are there, because you know that they have been trained in so random or common images, and your problem is like satellite images or detecting tumors in X-rays, and you always think, okay, maybe I start from scratch training the model, it will be better, but at the end it's always better to take pre-trained models. Isn't it?
I wouldn't say that it's always better, but in our case, it really turned out that pre-trained models performed much better than us, and also it was a lucky shot to try to create your own network, right? I mean, that's normally not a good idea, because very smart people thought about how to design a convolutional net, how many layers it should have so that it performs very well. But again, we just wanted to try. We wanted to get the most out of these images, but in the end, it was really pre-trained weights and efficient net also as a pre-trained model. About the hyperparameters, again, you had like how quick you learn and all these other knobs that you can turn. And in the end, I think it wasn't really such a big difference on how quickly you learn or not. It was more picking the right neural net and picking the right actually data set, so that you had a sensible problem that you were confident you can actually answer with your model. I think that was the biggest thing to decide and the biggest thing to do. It was not really do I have a learning rate of 0.6 or 0.95 or whatever. You could pick sensible values, but it was more that the problem is very well stable.
Okay. So, yeah, next point could be maybe about model evaluation. Well, yeah, before going to the product, but yeah, the model evaluation, maybe you already talked about it, but I don't know if you have something else to add. If you had to go, well, you go back many times after evaluating every model, you go back and decide to do changes in the model and so yeah, more or less we already talked about model evaluation. I don't know, maybe yeah, maybe we can go to the slide 6. So the building of the application.
Yeah, so this is where it becomes really interesting, because it was really also very other people involved than us data scientists. So we actually here at ERNI, we were very lucky that we have software developers, we have UX designers that could actually help us to make from this initial idea and from this initial algorithm to make really a challenge and distribute it. So actually to run it 24/7, obviously you needed people that coded in a very robust way, that deploy it, people that think about how will actually people experience it, how will they use it, and how can they learn from it. And I think that was very, very nice for us to learn more about this impact. And if I look back and look at the first model that we did, it was really not even similar to this nice UX and design challenge that you see today. It was really different, and I think that improved also the overall outcome of this GeoML project tremendously.
So there were no only communication between you two in the data science part, but also a lot of communication with this front end and UX people. So what did you learn? Like some examples of interesting things that you learned in this project about UX or front end that you didn't know before?
Well, let's say as Thomas was saying, it was very enriching, this experience, and also which makes it even more important structurally in a team and in a company, that you have this widespread distribution of skills. Because the challenge number 6 is to say, okay, how do you bring it into production? Because actually what we did was the back end and all the, let's say, the scientific and the models and the data science, but this was a prototype which was, let's say, working, but the aspect, okay, of making it work on the cloud and everywhere, yes. The other one is we were not spending so much time on making it looking appealing, and this was, for us, let's say, at least for me, was coming from research and a technical background, this type of aspect on how do you communicate and how should it feel, and making an introduction video and so on. This was a very pleasant experience, because actually is like having different, let's say, companies within one team, and there's like having a subscale project with many parties.
It looks like a big company, but it feels like inside like a small startups that are like collaborating.
Exactly. So it was very nice, and you could also see that we as data scientists very often forget certain things. So, for example, when we are showing you the image before that, we had to reduce the number of pixels just to make the algorithm train properly, that we had the right cutouts. When we presented it the first time, the UX people were like, "Oh, but use the nice images, right? Why is it so pixelated? Don't you have better images?" And it was for us, because we take it for granted that people understand why we have certain resolutions. But actually, from these interactions, we learned a lot. How can we present it better, and how we have to tell the story, why the pictures look how they do, and how can we show people what we actually did and how people will use it. And this is really not something that comes very natural for scientists, because we have messy plots, ugly colors very often, and that's not very appealing in the industry.
Yeah, that's one of the biggest change between academic background and working for a company that it's nice to have a good model. Is really important to have an accurate model that fix our problem and can solve our needs, but also is as same as important the way that we communicate and the way that we use the model. Is a shame that have a really theoretical, really complex model created and having save it in a pickle. We have to make it and put it on a production and keep working with the life cycle of the model, know how we have to retrain, when we have to retrain, and this is a really complex part and a really important part that normally some data science forget or don't are more related with, and this is really important also to do that.
Absolutely, yes.
Yeah, it was very interesting for us, maybe just as a small, because actually Thomas and myself, we started, we were just 1 month apart from the starting date as a data scientist. And basically we were looking the work from the scientific part. And then, of course, it was a bit, let's say, a lot of differences, but even between the two of us, and to say, okay, one concentrate more on the importance of the question itself, the other one is the importance of the methodology, and then there are data engineers which concentrate on the coding style and so on, and very, very interesting ecosystem. Yes.
So also to speak a little bit more about the front end of the app, because we have been talking so much about the machine learning part and the back end, because we are all in this part, but if you can give for the audience some details about which technologies they use to build the app and the cloud and so, just some details that you may know.
Yes, so this was done the front end with Angular, the framework, and it was done on the Google Cloud, the deployment with using Firebase, and the design, let's say the appearance has been done with Figma, which is a tool for design and so on, and then basically the UX design person in ERNI could basically give the Figma model to the front-end developer, and then it could basically work from there. And then this interface was very effective. So basically, the first design on the front end was done in a couple of days, and this was very, very nice because suddenly the front end developer and the UX designer, they were using both of them Figma, and this was a very nice match.
So for me, what was very interesting in that part was actually that we started out really as data scientists. We were really interested in getting the best out of our model, making good predictions. And then somehow during that project, actually our focus shifted, and it was more communicating also between the teams. So it was communicating between UX and design. By the way, there are two different people, right? So you had one design people who tried to make it really look appealing and catch people's eyes, and then also one UX person who tried actually to increase actually the user experience in a sense. Or will people actually press that button? Will they actually think about interacting? Is that too complicated? So it has many different levels. It's not only colors, or it's not only buttons. It's really a interesting mix. And then on the other hand, you also had a person who said, oh, I cannot implement it because that doesn't work. Or then we had to go back and say, yeah, but that's not the idea. We have to change it back. And so as more the project evolved, we were more like also organizing and trying to communicate what is the vision, how can we do it. And it was a very interesting time, and I think we had a lot of fun doing that.
Great.
Yeah, there is also maybe the last, let's say, discipline was even once you have this, let's say, product, is the marketing part. for example, this type of event and so on. This was another dimension where basically even the marketing team was involved to say, okay, how do you bring it outside of the office and so on. And let's say basically from data science, it went back to communication science, project science. Yeah, it was like a crash course into like an entire department of work.
So you started as a scientist or data scientist, and you shifted then to more to the product part of it, a product owner and even product manager and even marketing,
exactly.
like how to sell it. Okay, so really interesting. Maybe we can go to the next step or even the last slide.
Well, first of all, we have a question that is interesting and is related about what we are talking right now about marketing, front end, and whatever, which are not our main, our main department. And Michele asked if how many people were on the team.
Yeah, we commented it in the beginning, but maybe she wasn't there, so yeah, we can repeat it.
It was actually, I would say 7 or 8 in total.
7 or 8?
Like,
okay.
Yeah,
So
during
two
the
in data
entire
science, 2 in UX the front end, and then 2-3 in marketing, isn't it?
No. So it was in data science. We also have to say we had also another team member in data science. 2 other team members in data science being involved in that. So we have 4 data scientists, not working always all the time because we also have been on mandates sometimes. We were actually lucky at that time we could spend 100% on GeoML, so that was great. But yeah, I would say 4 data scientists, 1 designer, 1 UX, 1 marketing. That was basically the biggest. And then, and of course, the front end developer. So we were roughly 8 people.
Okay, yeah,
Okay.
that's the question. So we can go, maybe not this one, maybe go to the last one, this the summary one. Yeah, so maybe we can do a quick summary before ending because it's been like an hour and 10 minutes already. But yeah, let's do like a summary if you want, Tomas or Michele, like to understand from end to end how data science project is having this as an example, but how a regular one could be.
Yeah, so I might start, you might add whatever comes to your mind. So actually we have here this little cycle you can see. So it should basically show that it's never a straight line, right? You always have to go back and forth between your model, your idea, and actually when you try to deploy it, you can always go back even to the beginning. So you always, so for us, the biggest challenge was you have a lot of data. Make first sense of it, make reasonable data, clean it reasonably, come up for a problem that you can actually solve with an algorithm, adjust the algorithm, go maybe back to the data, change the data. I mean, not cheating, but changing like in I have to add a feature or I have to reshape the stuff. So it was a constant communication between all the parties. And I think that's what makes a data science project so interesting because you can go from the end when you already are thinking about designing the app, you can go back to the data and say, hey, do we need actually to have a better resolution so that people will be engaged? So it's a constant interaction, and that's why you see those loops, because you first have you have to formulate your idea. So you have some challenge, you have some data, and you have to clearly state, I have this idea. Then you have to take this idea and try to prototype it, try to make the first algorithms. And then once you have that, you have also to bring it in production. And from every step, you can really go back and forth. And I think that's also what is the interesting part of it, so that you can always change it and you have always to communicate. And I think that went actually really, really well here at the end. I don't know if you want to add.
Yes, basically we try to make this. At the end of the day, we made a full end-to-end data-driven project, even if it is not necessarily the commercial aspect, which was is in the foreground. But actually, we have these 3 steps, which is, as Thomas was saying, the challenge to have an idea, and then once you have formulated this idea, which might be business, a bit of data science, I mean, actually more business oriented, but actually once you have the idea to say, okay, how do you come with a proof? Let's say a proof of concept. And here in these first two circles is where basically very methodological and data science and so on. And proof to product is more into production, but actually at ERNI we are very lucky that we can offer basically this entire chain. Let's say the data scientists are more on the conceptual part, basically in the first and up maybe to the second circle, but actually to have seamless all the people involved. This is actually one of the something that for us is very important for having these end-to-end solutions. And this is actually how we also try to bring it out to the market.
Okay, really interesting. Also, yeah, these cycles are very interesting because you start with this business case, and sometimes it happens that you focus on the machine learning problem, problem, and maybe you get so good at that machine learning problem, but maybe then you find out that this wasn't solving the use case because the hypothesis was bad, or maybe sometimes you thought that you could predict accidents from satellite images, and it's not possible. Maybe satellite images doesn't contain enough information to maybe in this case we have seen that it's possible and it's great to see, but in other cases maybe you think, okay, with this and this input I could predict this output that is useful for business, and that's simply not possible. Sometimes for example, trying to predict stock markets, it's a problem really difficult to solve because it's very crazy and difficult to predict only from previous experience. That's a typical example of something that people think that if he can create a great machine learning model, they will be rich, and that's simply not that easy. It's almost impossible. For this reason, you have to always check that, okay, but are we solving the business case, yes or not, and going back if that's not the case.
Exactly, and also I think what you just mentioned, it makes it very interesting. Like, are we solving the problem? That's also a very scientific way. Like, when did you solve your problem, right? We also had a lot of discussions. How good actually does the network needs to be in order that we release it? How many games can we lose or win? How often has to be the network right? Sorry. This is not an easy question, and I think it goes back and forth. And just to let you know, I said we wanted to use this convolutional neural net, but on the way we also tried different things. I think at some point we had decision trees just to try to come up, can we say anything about the risk if we look at the colors in the image? Simply as that, right?
Really interesting. Yeah, really interesting.
So we had different approaches, and I think it was really nice that we had many ideas, and we always circled back and tried to really solve a question, so that we were not stuck on a certain algorithm or stuck on a certain data set, but we were more open to producing something that is really meaningful and that we actually can solve.
Okay, let's see if anyone else wants to make some other question. We are about to finish. I have now another question that we mentioned it in the beginning. So how transferable would be this model to, for example, if I put now some image from Spain, if I took some tile from Google Maps, for example, and I put it in the model, what do you think? It will be, it should be accurate or not? And what about some from USA or from any African country? So what do you think about this? How transferable it will be?
Should I?
Well, the question is whether it's a data science question, because actually the difficult part is it was very data intensive. The labeling of the data for the model.
I was referring
So
not
basically-
to retrain the model, but to with the same model to put only the image from
No.
Spain. You know, just to the inference part.
Yeah, I mean, you can do it because actually there are colors and images everywhere and streets. The transferability, yeah, you could say if there is a roundabout, I would expect similar, let's say, trends. But actually, you will not even be able to validate it because you need a lot of, let's say, traffic data and everything to to measure the metric itself. So this is actually the obstacle. To do inference, actually what you could do is basically try to interpret where the algorithm is looking into the image. And also Thomas was also looking into this aspect of to make it more interpretable. And this is actually the transferability of the insight.
Exactly. So actually, that's a very interesting question, and we want to work on it a bit more. So the project is not over. We really want to look into detail. Why does the network actually decide? And so maybe we find that in Switzerland, it's the case that roundabouts are looked at more. Maybe it's the green spaces. Maybe it's even how many houses do you have in the image. So up until now, we really don't know why the network decided. We want to open this black box, and we want to really look how a category is chosen. And maybe then we can also talk more about the transferability of the network, right? We maybe be able to say, okay, if we are in cities, in bigger cities that have very similar color ranges, roughly similar traffic, then you can use it there. Or maybe it's really totally different because people will drive different in different countries. So again, I think you really need to do first statistics, because also like when you go to the US, you probably have way more open streets, longer straight streets than here in Switzerland.
Yeah, and also, as you mentioned, it's not only the roads, it's the people that drive through them. So maybe the roads are the same, but people and cars and the legislation on car revision and so on, maybe only for that, it already changed, so it's important to understand.
Even the way of driving. I mean, all of us have traveling around the world, and there is not the same way to travel and to drive in each country. So it's a lot of things that we have to think about. And also the main important thing for the scalability of this model is that Michele mentioned. You are not able to evaluate the prediction because you don't have the data of the accident and this stuff to do if the inference was correct or not. So it's really difficult to put this model in other countries. At least in my opinion, I didn't make the model, so I don't know if I'm right or not, but that's the main problem.
Yeah, exactly. So this is a concept or a data drift that you have to be aware of. So if you train this model in Switzerland and you want to use it with the same train model, you want to use it in somewhere else, you have to be aware that you should retrain it with the data of that country. If you're not aware of this, you will commit like lots of errors. It's like a data drift, or more or less.
And by the way, just to make it very clear, I mean, you might forget it, and we also did at the beginning. It took us a while to figure it out. It's traffic accidents. It doesn't mean that always cars are involved, right? It can be pedestrians, it can be cyclists, it can be many things. So also this plays a huge role. So maybe some cities will have a completely different signatures, and so it's not only the driving style, but it's many things. So again, I would be very careful with applying this to other countries without really checking it and without having the data to double check.
Yeah. We shouldn't apply this not even in Switzerland for real. Of course. Yeah. Okay, so last question from my side, at least. I don't know if I just will have anyone. Which is your next idea, your next project? Maybe you won't have time for that, but do you have any next project? Maybe you don't want to tell it, but any cool idea like this one? Also, I will take what you said, that you have some externalities to do in GeoML. So you will bring them in 2 or 3 months in the internal coffee session. I wrote it down, so I take it. In 2-3 months, let's tell us what you find out. So the next ideas.
So next idea, actually for me, it's I haven't thought of any new project, but I think actually what is very cool is to open this black box and really see why a certain network actually decides how it decides, and maybe try to find new ways of showing this. So also the idea of show people what might be seen as risky or not. I think that is super interesting, and also to make a bit more out of it, and then use this insight. So, for example, there are many studies also by MIT or Harvard where they basically show that if you play classify certain things, it can be many things. I think I saw one study about cancer. If a doctor classifies images, it's not easy. If a network does it, it's maybe same or maybe better sometimes. But if you combine those two forces, they have much more prediction power. And it would be very interesting to see why this network predicts certain things and use it for our human advantage. So basically combine the two knowledges and make something better out of it. And I think that's very interesting.
Okay, yeah, explainability, very interesting topic. So yeah.
Yeah, and if I would add one aspect, maybe which might be a bit less technical, but more on the transfer, not necessarily of the network, but actually of the impact of the work, it would be on the communication side to say, okay, we use open source data, but actually to try to spread this type of message for the industry, to say, you don't always need very proprietary data and so on, but actually, even with some data science and very lean approach, you can maybe find something that is already very interesting, even with less resources. And this might be a narrative of going not necessarily to big data and all of this, but actually to try to have with some smartness, even to have the narrative of being effective on the usage of and having very small pilot projects without thinking about the huge machinery and cloud and everything, but actually trying to bring this sort of scientific acumen into some low-hanging fruits in the industry. And this is maybe not necessarily what you would expect from a data scientist and so on, but we see some potential, but actually is the art of communication here maybe the limiting part.
Yeah, so normally we focus more on the technical part, but these aspects that you mentioned are also really interesting and very important in this industry. Yeah, so I invite you in 2-3 months to bring this further investigation and so. I don't know, Jose, if you have any other question.
No, for me it's everything clear. I think that we have to make the point in that Michele say that there is not only the technical problems that we have to face in business. We have to know how to communicate. We have to know to be the people who say that artificial intelligence can help real problems and try to do in that way. But there is a question in the chat. Rocky Money asked, what can be possible scope of machine learning in GIS according to you, which can be constructed from open source data?
Yeah, let's say if you have GIS data, you have some, let's say, geospatial relationship between points, and the natural choice is to use graphs. And basically, there is like the discipline of graph neural network, which basically, if you have something that is as a nature of a network, then basically you have a spatial and temporal distribution. For example, traffic is this type of example, but for example, water piping and other stuff. And basically, machine learning with graph neural network is something that has been used a lot, for example, for Twitter, for this type of, let's say, relationship of having a semantic enhancement of the relationship. But the GIS is also, there is a lot of, let's say, logistics of information, which is as a graph nature. And there is a lot of work on this. And mathematically is not very easy, and it might become quite tricky to handle, but there is a lot of potential because everything is connected in reality. Then it's a matter of to find an effective way to find your features.
Yeah, so this field is also called not only GIS but also Earth Observation (EO), and it is huge, the potential of it, because with more and more satellites and more public but also private information, I think that maybe we have the industry hasn't even reached like the 10 or 20% of the full capacity of this of the Earth observation capabilities. There is lots to do, and in every industry, agriculture and many others, like traffic like this, or in nature. I've been also in some projects, and there is lots of things to do. So yeah, a lot to explore there. I will share now a link in the chat about our open positions in LinkedIn. If anyone wants to check them, if anyone wants to join ERNI, and if no one has more questions, I will leave it here. So make sure to follow us on YouTube and LinkedIn also if you haven't done it yet. And well, bye bye, and thank you for joining us today.
Thank you, Michele. Thank you, Tomas.
Thank you so
really
much for
good,
explaining us today.
experience.
And by the way, if you anyone wants to reach us, please just connect via LinkedIn, ask our questions also for GeoML. We are more than happy to answer.
Tomas Tamfal and Michele Bolla. Yeah, I think that in the link of the in the link of the Twitch session, the Eventbrite link was your info there. So yeah, feel free to reach us. Thank you very much, and bye bye.
Thank you for the invite.
Thank you.
Bye bye.
Thank you so much.
Bye.